There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. This is video 11. We're going to continue on scaling factor of dynamic variables, where it's all dynamic variables has a scaling factor. Okay, basically it's lambda squared, lambda minus 1. Okay, so this is the paper I put it on. I put a paper on ResearchGate. So why we need a scaling factor? We talked about that in the last video. It's basically weight of the tau, where it can describe the emitting pattern of virtual particles at different energy momentum. So basically, it's give of a cutoff function. Okay. Okay, we can use the scaling factor to design a cutoff function or limit which pattern, how much energy momentum give you a chance of emitting. Okay, so let's see what we're going to talk about this video in the self-interaction version of quantum mechanics. Okay, so we're going to talk about the virtual particles and limited energy of momentum can be borrowed, no infinities in the quantum field theory. Okay, so in this video we're going to also talk about the space-time of quantum mechanics. Okay. Okay, so we're going to talk about that. If we see that electron self-energy term, it's like that. Okay, so that's in the Feynman diagram where you have an electron, so emitting a virtual particle of momentum k and p minus k over here. Okay, so then that's the self-interacting term. That goes to infinity. So the trouble we're having is when we do a perturbation theory, we will have k to the power of n. When n greater than 0, k, when the integration diverge at when k goes to infinity. When n is less than 0, k divergent at k equals 0, at smaller k. So basically the perturbation theory, no matter what you do, you will have infinities. Okay. So fortunately, in the current quantum electrodynamics, we have limited number of infinities we can get rid of. But now when you go into QCD, okay, quantum chromodynamic or quantum gravity, okay, you have infinite number of infinities because all these Feynman diagram will give infinities. You have many of them, okay. So this is why a Planck term is important. So if we see the scalar factor, we already did show that in my paper. Okay, so this d4k has lambda equal minus 4. Okay, so this from the Dirac equation, lambda equals 0. K squared has lambda equals plus 2. So the mass correction term, that's delta m term, okay. Mass correction term has a finite constant of alpha, which lambda is minus 1, okay. So this one, it's the scale, it's not 0. The scaling factor lambda equals square, okay. So by introducing the k-dependent scaling factor to the above integration, like the Planck term, infinity can be removed. So let's see how it's been removed. So as I mentioned in the last video, okay, so this is like a temperature in the Planck term. The mass, the smaller the mass, that means the less energy it can borrow to you. Okay, because if m goes to 0, k is finite. Okay, finite. Okay, some numbers. This already goes into 0. Okay, so that means in the delta m, okay, if we consider there is an alpha in here, so we need a lambda cubic term. Okay, so now when we do the integration of this term, Planck term, or converge anything you have over here, because the beauty of the Planck term is when k goes to 0, okay, this term becomes small, because when k goes to 0, this goes to like small, like that term. Okay, they cancelled. This goes, lambda goes to finite. Okay, so when k goes to infinity, okay, this term goes to infinite big, then this whole term lambda goes to 0. Okay, so anyway, the Planck term, if you know some mathematics, or if you played with the black body radiation, you know they have the beauty of converging on both sides. Okay, so now this term is finite. Okay, so whether we are allowed this to be finite and to be 0, so if you integrate that, that's equals 0. Okay, so that's the integration if you do play with the integration. Okay, so but that's delta m equals 3 alpha over 2 pi and log cutoff over mass. Okay, that's the current, okay, the current physics. Okay, okay, but in our presentation we already see that lambda can only maximum can be m, so the cutoff function equals m, so this goes to 0. Even with our integration, we don't have this. It's like a cutoff function. Okay, or we call it a distribution function. That means how much energy momentum you can emit as a virtual particle. You cannot borrow infinite because you have m limited on your behavior. So that means our electron, it's like a black body. It has internal structure of emitting a certain pattern of virtual particles. So this function of cutoff function or distribution function, it will reveal the internal structure of electron. That means we can use these factors, and by studying, by comparison, all the behaviors of electron in different possibilities, configurations, so we can study the internal structure of electron. I mean, if we do the same for photon, we can also see the internal structure of photon. So the elementary particles now all have internal structures. If we see that in the self-interacting field theory. Okay, so we already talked about this in the last video. I'm going to briefly go through this. So now, by introducing the scaling factor, people say, hey, Q, what we are doing the Fourier transformation when we do the equation. Okay, so now what we need to do mathematically, we need to do from the Fourier transformation when we do quantum mechanics to Laplace transformation. Okay, so that means when we have, let's say, the quantum mechanics, the operator, we see that, I mean, if you know some quantum mechanics, that's your starting point. Okay, You define the momentum and its eigenvalue of this operator, okay? Once the scale factor is introduced, we have something like that, okay? Which H0 is a true Planck constant, because now we are introducing a scaling factor because H has a scale factor of 1. Okay, so that's why I'm writing over here. So if we re-gauge the energy momentum of Fourier transformation, if we do something like that, so the wave function of this one can be rewritten something like that, which is Laplacian transformation. So without introducing the scaling factor, we can use Fourier transformation, but we need to introduce a scale factor, or we do a Laplace transformation. So what we do, we absorb the scaling factor into the Laplace transformation. So in the future, what I hope that all quantum mechanics, we're going to talk about the Laplace transformation instead of Fourier transformation, because that will bring the distribution or the emitting pattern of the virtual particle into the Laplace space. Okay, so the scaling factor is been introduced into the Laplace function. Okay, so why its scale factor is needed? Because we think in our self-interacting field theory, we think all elementary particle has internal structures. Okay, so in the 1900s or in the early 20th century, okay, Bohr, Einstein, and Planck, okay, the quantization of electromagnetic waves revealed the interior structure of our atom, okay. So now we have a scaling factor. Let's study that, okay. We are going to reveal the internal structure of elementary particles. We will see how the internal structure of electron, how their field be moved around, okay, how they emit in the different particles, okay. So if we introduce in the same thing to the protons, and then you will see many excited states, because in the 1900s we see the electron movement. We have a nuclei over here. We have an electron move like that. Okay. So we see the structure of the electrons. Now what we're going to see that, okay, so let's say we have a proton, okay, proton over here, okay, so it will have many excited states. Then we will have all these many more particles, elementary particles. We can have many more layers of the electrons, different structures, different electrons excited states, or S states or L states, something like that. Our particle, fundamental particle, will also have different excited states. That's why our particle physics see many different versions of the particles. When I was talking to some friend, they said, "Oh my God, there's so many particles." Yes, there are different particles. That's because of they are in a temporary excited states, or their internal structure being excited. Okay, just like the electron being excited like that. So, but the self-interacting field theory gave different mass to different excited states of the particles, okay? But different shelf life, how it jumps back and forth. When we have electron move up and down for different orbit, we have different atoms, okay? Now we will have different particles. Because the self-interacting theory, because of their self-interacting, they may generate different mass, okay? So, but if we can weight of our atoms, we see that also it has energy of the different orbit, but this energy very small. But the self-interacting scale is much bigger. So this is why you will see different mass. instead of this one atom hydrogen has almost a different orbit, they have the same, about the same mass. But now our self-interacting field theory will have different mass because it's much stronger. Okay? So let's bring the quantum mechanics and general relativity together. Okay? So we are defining the momentum like that. But that in general relativity, okay, this is general relativity. This is quantum mechanics. Okay? So in this section, we're going to talk about the space-time property of quantum mechanics. Okay? This is general relativity. This is quantum mechanics. Because they are both describe the momentum. Okay? Let's times this on both sides, we have that. Okay? So then we find that d tau equals like that. Okay? This term is just like if we see the geodesic equation, what we have is we have an extra term of okay, let's write out that d tau squared, okay, plus okay. Okay, so that's, you see, we see this term. Okay, that's what we see in the geodesic equation. Okay, but that's from quantum mechanics. Okay, very interesting that it has an I in here. This became imaginary or complex. Okay, sorry, that's a complex. But all our general relativity equation were in real domain. Okay, all the variables are real. But now we have a complex. So, like the scalar part of the general relativity, but it's a complex space-time. Okay, when we first saw the Schwarzschild solutions in general relativity, because at that time d tau squared. Okay. But now if we take the d tau like that, we see a square root of that, dt. That means if we measure the four-dimensional space-time, okay, but at one point, then dx equals 0, okay, dx equals 0. So that's why we have that. If we have 2gm over r squared in the Schwarzschild black hole, if it's greater than 1, that means it's stronger than the black hole. It became a complex. Okay, in the interstellar movie, in the movie, they talk about the daughter and the father meet because the space and time change. So, but I don't like that idea. Okay, so what I think, what we see that it's once it's stronger than black hole, it became a complex. Okay, we see that it's a complex, but when we study the elementary particles, it's already a black hole. Okay, so it's a black hole. Now if the field became stronger, it became a complex domain because this is greater than 1. Okay, if this is greater than 1, this became imaginary. That's d tau became complex. It's understandable. Okay, so this is where we see that the d tau is a complex number. Okay, so if we rewrite that, I mean, in the classical quantum mechanics, the energy is not just that part. Okay, it has a mass in there. Because this phi depends on the speed of the particle, we have a complex Finster spacetime. Okay, because this is a Finster spacetime, it's a complex. Okay. Now we see that quantum mechanics It also has a space-time structure like general relativity, but it's complex. Okay? It makes sense because we're studying outside a black hole. Because our microparticles or elemental particle is a black hole, okay, of self-interacting field theory. Now we're studying something extra. If we put it into the black hole, that means you see the complex structure because the square root of the d tau. Yeah. So if we rewrite that, we expand that into a real part and a complex part. Okay, so we rewrite the space-time into two parts. Because it's complex, we have the real and the imaginary. Imaginary space-time, okay? So, but the imaginary space-time, now all this part is real, this one is imaginary. This companion space-time, we have, because of Finster space-time, now we have two parts. One is the real part, one is the virtual part, imaginary part, okay? But the imaginary part has a coefficient in here, okay? But the d tau over here has a 1, okay? So this is much smaller. It's about 10 to the 5th to 10 to the minus 7th, okay? Our quantum mechanics scale is like that. So if we know the h, the Planck constant, it's 197 MeV, okay? So the time scale is like that. So if we put it in here, so we will see that this is about 10 to the minus 5th to 10 to the minus 7th, okay? So if we measure the time, okay, we have time part over here, we have space-time part over here. If we measure the time of the imaginary part, it's much smaller, okay? So that means even to us it's 100,000 kilometers. But the companion space-time, it's much smaller. It's about 1 kilometer, okay? So the scale is smaller. That means time is smaller. Speed will be faster, okay? So that means we assume the quantum mechanics and space-time put it into like a general relativity, okay? So we see that you have a real part and the imaginary part. The imaginary part will be smaller, okay? And because the distance is smaller, to us will be much faster because the time is smaller. Also, let's say it takes us 1 second from one place to another one, okay? But then the companion space takes 10 to the minus 5th second. So that means if we spend 1 year, local time to us is 1 year, in the companion space is much faster, okay? Take much less time, okay? So now we see that we have the quantum mechanics and all this into a new space-time which has a companion space-time. In the future videos, we'll come back to this, okay? So, but for this 15 video, we just leave it over here, okay? So, what we see that also, because of we see this in the self-interacting field theory, we can exchange particles, okay? If we exchange the field energy a lot, is this quantum entanglement? Okay, because of the companion space, okay? It's much smaller scale or much faster. So that means in this space-time, if it's virtual or imaginary, so then they exchange energy and momentum much faster than what we see. I think that's a quantum entanglement. So the virtual particle space-time, it's different by a factor of like that. So if we exchange some energy momentum between the two particles, we have an extra term in the Feynman diagram, okay? okay, the extra term, which are related by a factor of like that, okay. So I think that's the entanglement state, okay. So in this video, we put relativity and quantum mechanics to see the quantum mechanical behavior. We found a space-time, combining space-time, which is 10 to the 5th time faster than our space-time, okay. I think that's why we see a entangled state at much faster speed, okay. Yeah, it's a complex space-time. We were going to show that in the future videos, okay. So from these two videos, we basically bring the scaling factor in. We are solving the infinity problem. We propose that some of maybe the entanglement state. This is a preliminary assumptions, okay. I didn't do detailed studies. We're going to show that in the future videos, okay. It will have also some implications, okay. So now from the next video, we're going to continue our self-interacting field theory. That's a direction I'm going to be mostly focused on, okay. We're going to define a difference tensor to replace the affine connections. So we're going to derive the tensor version of the self-interacting field theory. So we're going to propose a modified general relativity. Okay, thank you.